Greetings and welcome back. Today we're going to continue our discussion of electrophilic aromatic substitution by looking at the groups on a benzene ring that could direct where your electrophile is going to show up. So for instance, if we start with benzene and we add to this Br2 and iron bromide, then we are going to remove a hydrogen and replace it with a bromine. If you're just starting with benzene, it doesn't matter where that occurs because all of those locations would be identical. However, if you have a group on the benzene ring in the first place, therefore, if it is not really a benzene ring, so something like toluene, which would be this guy, then you have multiple different places where the bromine could show up. And so the product would have that bromine attached to the benzene ring, but the question is where? So we'd have a bromine attached somewhere, but that's what we're going to be looking at today, is how do groups already on a benzene ring impact the location relative to where that electrophilic aromatic substitution product is going to occur. Let's jump right into the example of an alkyl group. So if we have an R attached to that benzene ring, where would you have electrophilic aromatic substitution show up? And what I'd like you guys to do is to draw for that specific example we just did, which is that CH3. So draw the three possibilities for this reaction. So if we're putting this in with bromine and FeBr3, we would make that complex, which has a really strong bromine electrophile. Look like this: iron minus, bromine plus. And one of these double bonds is going to add on to that bromine. So what I'd like you guys to do is to go through and look at what are the possibilities for this reaction. And we will do, there's kind of three of them, because you could put the bromine on ortho, which would end up right here, or meta, which would put that bromine on right there, or para, which would put the bromine on right there. And the answer to where this goes has to do with that intermediate. So if you would, draw out the mechanism, pause this, draw out the mechanism including all resonance structures of every intermediate for each of those three pathways. It's going to be quite a bit, so pause this and come on back whenever you're ready. Alright, so let's walk through the mechanism for the first one together, which is the one we've drawn in pink. If we're putting the bromine onto that position right next to the CH3, then our intermediate would look like this, and the carbocation would be right there. We would have multiple resonance structures of the intermediate here, because we could push those bonds around that ring in order to spread out the positive charge. And so in the first one, we would hop it over that way. Then we would have a double bond here and here, and the positive charge there. And we would keep going one more where we could push it over like that. That would result in positive charge being right here. And this may look pretty much identical to what we've done already, but notice the location of the carbocation. In this one it's a secondary carbocation. In this one it's a secondary carbocation. But in this one we have a tertiary carbocation, and the reason for that is the location of that CH3. So the methyl group right up here, because of its location, if you put the bromine on in an ortho position, it would give you a tertiary carbocation, which is much, much, much more stable than secondary or even primary, although primary would not be a possibility here. So the second step of this would just involve that whatever your base is, which in this case would just be that FeBr3. Oops. Of course, that iron has a negative charge, so it wants to kick off one of those bromines. The bromine would grab that H, and we would restore our aromaticity. And the product would be, you'd have your benzene ring back. And in this case, the bromine would be ortho. So if you drew out the mechanisms for all of the other possibilities, so in essence the one that I have shown in blue, which would give you a meta product, or the one I've shown in green, where we would put the bromine on that product para position. And if you didn't do that, you're welcome to stop and do that now. What we would see is that if you have an R group already on the benzene ring, we say that that R group is ortho-para-directing for electrophilic aromatic substitution. And what that means is that we are going to be able to do electrophilic aromatic substitution actually much more quickly because we have a much more stable intermediate. The intermediate, if you put your bromine on, or whatever you're doing, nitration, sulfonation, whatever, for electrophilic aromatic substitution, anytime you have an R group, it will direct your addition to occur at the ortho position or the para position. If you go through all of these mechanisms, you would see that if you try to put it on the meta position, you would not be able to have a secondary carbocation intermediate. Therefore, it doesn't make meta any better, but it makes ortho and para much better. So what it would do is it would increase the chances of you putting that substitution or putting on the substituent or doing the substitution reaction at both the ortho and the para position. If you ask which one is better, really neither is better. However, you have two ortho positions and only one para position. So unless you have a really bulky R group, you tend to get more product with the ortho substituent and a little bit less with the para substituent, way less with the meta substituent. All right, so that's how alkyl groups work. They are ortho-para-directing for electrophilic aromatic substitution. What I'm going to give you right now is kind of the scale of how these guys direct electrophilic aromatic substitution. So all of this is going to be for electrophilic aromatic substitution. Because it increases the or decreases the energy or increases the stability of that intermediate, these guys also make electrophilic aromatic substitution go faster. So we say that they are activating for electrophilic aromatic substitution. And that was that benzene ring. All right, so, or sorry, an R group on your benzene ring. So any R group is going to fall under kind of the umbrella of activating, and it's also going to be ortho-para-directing. All right, but any groups that have nitrogen or an oxygen with a lone pair, it turns out, are also going to be activating, and they're also going to be ortho-para-directing. However, these guys are even more activating and even more strongly ortho-para-directing. So here are the functional groups that I would be concerned about. The ones that you would see the most in this case would be a nitrogen, so an amine, the nitrogen of an amide, the oxygen of an ether, or the oxygen of an alcohol. Those guys are all going to be activating, meaning they make this reaction go faster. And furthermore, they're also going to be ortho-para-directing. So all of these guys here are activating and ortho-para-directing. And again, this is for electrophilic aromatic substitution. So we're talking about if you have something on the benzene ring already, how does that impact the location of the reaction itself? So you're putting on the second thing. Halogens, so any halogens, chlorine, bromine, iodine, or fluorine, are going to be ortho-para-directing because of the intermediate, but they're going to be deactivating. That is to say, they would slow this reaction down. So it's much harder to get electrophilic aromatic substitution to work if you have a chlorine or a bromine or an iodine or a fluorine on the ring. And I'd like you guys to do all of these and tell me why in class, but That is the answer, is that they are deactivating, but they're still ortho-para-directing. Carbonyls of any type, so whether they're carbonyls of a ketone, carbonyls of an aldehyde, carbonyls of carboxylic acid, or the carbonyl of an ester, these guys are also going to be deactivating, but they are going to be meta-directing. So if you have a carbonyl on the ring, it is going to make that second substituent show up at a meta position. So what this means is if we started with like benzoic acid, so just a benzene ring with a carboxylic acid on it, if we then take that reaction and let's just do chlorine, so Cl2 and AlCl3. That would be electrophilic aromatic substitution that would add on a chlorine. But because the group that's on there already, which is a benzoic acid, falls into this meta-directing category, then your chlorine, when you put that chlorine on, is going to show up meta to that group, or meta to the carbonyl, which means that your major product would be this one right here. So notice that that chlorine is meta to the benzoic acid. Lastly, we have this group of things that are positively or almost positively charged, which would include a nitro. If you draw out the nitro, the nitrogen has a formal plus charge. A protonated amine, so an N with a plus charge, or a nitrile, a C triple bond N. Those would be deactivating for electrophilic aromatic substitution, and they would also be meta-directing. Alright, so what I would like you guys to do is to pick one example from each of the categories that we haven't done already. So do one example of just one of these. Don't worry about halogens. One example of one of these, and one example of one of these, and work through the mechanism. Don't worry about para, just do ortho and meta for each one. So that will be 6 mechanisms. So pick one over here and draw the full mechanism for electrophilic aromatic substitution at the ortho position and electrophilic aromatic substitution at the meta position. Do the same thing for one of these. Pick out which one you like. You can do this one if you want to. And show me the mechanism with the intermediate, all its resonance structures, for ortho and for meta. And then finally do the same thing over here. And what I'd like to talk to, because you guys have all the skills to do this, is why. Why are these meta-directing? Why are these meta-directing? And why are these so strongly ortho-para-directing? The last little twist on this is, what if you have multiple groups on that benzene ring? So let's say that we have a bromine on here, and we have a methoxy group. What if we do nitration of this? So I'm going to put this in a little bit of nitric acid and some sulfuric acid, and what it will do is add on a nitro group. Well, the directingness of these is such that methoxy directs ortho-para, so the para position doesn't have a hydrogen, so we couldn't do it there. So it would direct ortho to itself. The bromine is also ortho-para directing and would direct bromine, or the substituent, ortho to itself. And who wins? The answer in this case is the most activating substituent does the directing. So whichever substituent is most activating, you can think about that as the one that is kind of gives them a stronger preference, directs the electrophilic aromatic substitution. Therefore, it's the methoxy group that would essentially get its way, and your nitro group would show up where it wants. So in this case, you would have the nitro group right here, because it is the strongest or most activating substituent, which would be the methoxy. Those oxygens were the furthest to the left on that last slide. They're the ones that kind of have the strongest preference, the strongest activating, and they're the ones that choose. So therefore, in this case, that nitro group would show up ortho to the methoxy group. The bromine, unfortunately, doesn't get any say into this whatsoever. All right, thank you very much, and I will see you in class.